Hello, this is Dr. Olson again. Um, I'm here to complete a discussion on energy and heat. We have been discussing not just energy and heat, but specifically heat, which is a transfer of energy due to a change in temperature. And because of this difference of temperature, energy is transferred, resulting in either a change in temperature or a change in the state of matter. With the change in state of matter, we already discussed latent heat. This video, we are going to address changes in temperature with heat. There are three ways that heat is transferred, resulting in a change in temperature. The first form is conduction, the second is convection, and the third is radiation. We'll start off with conduction, which is quite simple. Conduction is the transfer of energy one molecule to another. Simple way to think of this is playing billiards or pool. When you have one pool ball moving along, it has energy. It hits another ball that is stationary. All of a sudden, the cue ball stops and the ball that it hits starts moving. The energy was completely transferred from the cue ball into the other ball, which is now moving. The same method happens with conduction. The important thing to remember about conduction is that, on the whole, energy transfers from hot to cold. Energy will never move from the cold to the hot. Now, when we talk about how energy travels hot to cold, the question comes up, how quickly will it move from hot to cold? How quickly the heat transfers through an object depends on what the material is made of. The property of the material that determines how quickly heat is transferred is what we call heat conductivity, or the rate at which heat is conducted. Good example to demonstrate heat conductivity is cooking. When we cook, sometimes we use metal spoons, but sometimes we use wood spoons. Often we use wood because, as you can see here, wood has a very low conductivity. Having such a low conductivity, it takes a long time for heat to transfer molecule to molecule through a wooden spoon. Whereas when you have a metal spoon, which is stainless steel most of the time, you're talking about a much higher conductivity. Actual silver has very high of 427. Stainless steel will probably be closer to iron, which is 80. And since it has such a high conductivity, heat is transferred very quickly. So when you're cooking with a metal spoon, often the spoon will get hot while you're cooking, and that's because it has such a high conductivity. This is one reason why we prefer wood instead, is because it will not heat up quite as quickly. Now, in terms of the atmosphere, this is important because air is a very, very poor conductor. It conducts heat even worse than wood. Air is not very good at conducting heat. Therefore, conduction is not the primary method of heat transfer in our atmosphere. The second type of heat resulting in a change of temperature is what we call convection. Convection is the transfer of energy with the movement of a gas or a liquid. Good example of this, you're sitting in a swimming pool, enjoying the nice warmth of the pool, and then all of a sudden, just sitting there, all of a sudden the water turns cold. What's happening is the warm air or warm water that was around you suddenly, for some reason, moves to another part of the pool and is replaced by cold water. That warm water moves away, taking the energy with it. That is the whole principle of convection. The energy is moved as the liquid or gas itself moves. As far as the atmosphere goes, an important point to remember is that when warm air rises, and as it rises, it expands and cools. But then cold air sinks, and as it sinks, it contracts and warms up. And we can see that demonstrated in the middle figure here. So how does convection work in the atmosphere? Let's say that you've got a hot surface, which is shown here in the center of this figure. That warm air, as we just discussed, will want to rise. The warm air rises and expands. But then you have cold air from above, which is going to want to sink. So you end up with a pattern of warm air which rises, and then cold air which sinks. And you end up with a circular pattern. This is what we call convection circulation. It is a cycle of air due to the rising of warm air and the sinking of cold air. One added point of convection is when we talk about convection right along the surface. This is what we usually have to deal with since we are on the surface, and convection right along the surface horizontally is what we call advection. So when you see that term thrown around throughout the course, you'll know that that's what it means. We're talking about convection horizontally near the ground. So we can talk about what we call thermals. A thermal is when you have a little bubble of air which happens from heating the surface. So as the sun heats the surface, you have hot air which wants to rise. As it rises, it pretty much forms a little bit of a bubble, which, since it's hotter than the air around it, wants to keep rising. The thermal becomes part of the convection cycle. Now, how do we know when we have thermals? I apologize, I thought I had one more picture here. The way we can tell when we have a thermal is when this thermal gets high enough, it cools as it rises, and as it cools, it condenses and forms a cloud. We'll talk in Chapter 4 more about the different types of clouds that are formed. The third type of heat resulting in a change in temperature is what we call radiation. Now, radiation kind of has a bad name to it due to high energy radiation, nuclear waste, that sort of problem environmentally. But really, that's not what radiation is. That's part of it, but not the complete story. Radiation is the transfer of energy through any electromagnetic wave. One type of electromagnetic wave is actually light. All the light that you see around you is radiation. Now let's talk a little bit more about these electromagnetic waves. It is a wave of electric and magnetic fields, hence why it's called electromagnetic waves. Now, when we talk about waves, we need to talk about wavelength, which is the distance between the two crests of a wave. When we talk about electromagnetic waves, the type of electromagnetic wave depends on the wavelength. So, for instance, you have radio waves, which have wavelengths of typically 10 to 100 meters. And yes, radio waves are a type of radiation. Another type of radiation is microwaves, the very same microwaves that are used to heat your food in a box, which we conveniently call a microwave. A microwave is an electromagnetic wave that is about a millimeter long, or 1,000th of a meter. Infrared waves are about a millionth of a meter, or a micrometer is what that's more commonly called. Visible light is also an electromagnetic wave with a very, very short wavelength. We're talking on the order of hundreds of nanometers. Once you have shorter wavelengths, you start talking about ultraviolet waves, X-rays, and gamma rays. The X-rays and the gamma rays are the ones that cause the most problems. This is because the shorter that your wavelength is, the more amount of energy can be stored in that wave. So X-rays and gamma rays, since they have such short wavelengths, they carry more energy. This is why when you go out on the beach, you can get sunburned because you are being bombarded with ultraviolet waves, which have short wavelengths, therefore high energy. Every single object in the entire universe, if its temperature is above absolute zero or 0 Kelvin, will radiate energy away. It emits energy through electromagnetic waves. Now, what type of wavelength it emits depends on the temperature of the object. Here is an equation on the bottom right of your screen saying that the wavelength, which is indicated by this upside down Y looking character, the wavelength of radiation is going to be some constant number divided by the temperature of that object. So as the temperature increases, the wavelength decreases. So hotter objects such as the sun will emit more short wavelength radiation, ultraviolet waves, visible light, so on. And colder objects such as the Earth will emit longer wavelengths such as infrared waves. Here is a spectrum of the different electromagnetic waves emitted by the sun. You can see that the peak wavelength of sunlight is actually green light. That is determined by the temperature of the sun itself. Other wavelengths are also emitted by the sun, but typically the most abundant wavelength from the sun is actually green light, and next to that would be blue light, violet light, yellow, so on. Now, as we saw, the amount of energy in wavelength in radiation depends on the wavelength. The shorter the wavelength, the more energy there is. So here on the left of this figure, we're showing the peak of the sun's solar spectrum. And you can see the intensity of radiation, which is a measure of the amount of energy. It's quite high, 10 times 10 to the 7th, so quite high. The Earth also emits radiation, but because it is colder, it is a shorter, colder means a longer wavelength. We're talking about infrared, and the amount of energy is 24, whereas before we were talking about a much, much higher number. So the colder an object is, the longer the wavelength, and also, as you can see from the equation above, the colder an object, the less radiation it also has. Converse is also true. The hotter an object is, the shorter the wavelength, and the more energy is included in that radiation. And that concludes our discussion on energy and heat. Next video we will talk about the energy budget, which is the balance of incoming energy to the Earth and the atmosphere balanced with the energy that is escaping the Earth and the atmosphere. And we will talk about that in the next video. Any questions, please always feel free to email me, call me, whatever, and I will be happy to answer.